Hello, IB Physics students, Ms. Getz here. Today for our sub day, I've decided that I don't I don't think it's going to be super helpful for you to move forward with the new lab for our next unit without me. So I have a little support video for you here about your IA. And I want you to watch this with your lab group and then check in as a group on what you have calculated for your values for your slope and for your y-intercept and how do they compare with the theoretical values that you hopefully calculated earlier on. And if you didn't, you can still calculate those theoretical values now. So we're going to be talking a little bit about our lab because again, your homework, your assignment from last week, that is the due Thursday before class, let's say, is to write up the data analysis section and the conclusion section for your friction lab. And so the data analysis section we've practiced writing up before. I have a lot more detail that I'm going to point out to you on Schoology in a little minute. But I also have the IB rubric, so you can get a sense of what IB says about this. And then I have my much more detailed checklist that can give you, again, that additional detail when you're kind of confused about what one of these descriptors means, because the communication of the recording and processing of data is both clear and precise is honestly not entirely clear to me. What do they exactly mean? And I've worked with other IB physics teachers to create that for you, and we've used it a little in class, but I have an updated version that I'm going to show you in a bit. But you have collected your data, you have analyzed your data. So your data analysis part is done. You're just going to formalize the writing of it in your lab report. Because again, the IA is a formal lab report. So you're going to do the data analysis section. That's formalizing that analysis that you already did. And then you're also going to be adding on this lab, the conclusion section. And the conclusion section is a new part of the IA. It wasn't there for previous students. And it is a part of the IA that is actually really easy to just ace. You can just crush it here because the conclusion is really where you are saying, here are my results. This is what I got. This is how precise it is, how accurate it is, based on the accepted scientific value, the accepted scientific context. And so you might say, oh, wait, Ms. Getz, that's the part that I'm confused by. And so that's the part that I have in this video that I'm going to sort of walk you through. So in class, we went through the beginning of the lab together. We looked at the IA together. We looked at that first section, which is called the research design, and you went through and you filled in the blanks, and it was pretty challenging. Thinking about how you're going to combine your equations together to get this final equation down here, equation 7, for what we expect our lab results to be. That the force applied is equal to the coefficient of friction times the mass original plus the mass added. So together it's the total mass multiplied by the acceleration due to gravity. So we combined a lot of equations together using our physics knowledge to get this final result equation. And so then from this, you should be able to actually say algebraically what the slope of the line should equal and what the y-intercept should equal, and then be able to calculate out what that means the slope and y-intercept actually equal as a number based on what we know about physics ahead of time. And this is the part that I think has been pretty challenging for people. So I went over this already once in class, but here I'm going over it again for you, and you can stop and replay and pause and ask group mates, wait, what is Ms. Getz talking about? Because you really want to have a good, strong understanding of this. So again, I've got this equation. That's that force applied. You are pulling on the force probe, and that is the force that you measured. So that's the thing you are measuring in this lab, our dependent variable. And from physics, from some of our forces and combining those forces together, knowing how friction is calculated, we can then get this larger equation, which again is this equation 7 right here in the lab. So I'm just rewriting equation 7 right here. And so then I can say, okay, well, equation 7, this looks kind of messy. So I am going to distribute the coefficient of friction and the gravitational acceleration inside these parentheses, because you don't want to have to deal with parentheses when you're trying to make sense of an equation and connect it to your lab results. And so I did that. Take a moment to make sure you really understand what I did. Um, I could have some parentheses in here. They won't be in here later. They don't need to be in here. They're irrelevant. Anyway, but I have just distributed the coefficient of friction and the acceleration due to gravity. So I've got this new equation, and I'm going to go along with this new equation, and I'm going to say, okay, great. Then I graphed two of these things. I graphed the force that I measured with the force probe, which you guys determined as a lab group, and you graphed the mass that you added to your little wooden block. So you added 100 grams, which 0.1 kilograms, you added 0.2 kilograms, you added 0.3 kilograms, and so on. And so you have a graph of those two things. So that means one of them is our x variable and one of them is our y variable. So I'm actually going to write directly above this the equation for a line, because when you graphed this, you got something that looked pretty linear. Some of you had a few hinky points, especially at the beginning, but it looked pretty darn linear. And so if I consider that the force that I'm pulling with is actually my y variable, so that's the thing that's on the y axis, and the mass that I've added, so I add a little bit of mass every moment, is my x variable. That means that anything that's left over in this equation, mu times g plus mass original, those are the numbers that I can actually get from my equation. Those are going to be numbers in the equation in the final graph that I make. And so that means that the mass, oh, that's not mass. This M stands for slope. That means that the slope is equal to the coefficient of friction times the acceleration due to gravity. That is what the slope of my graph is going to be. So whatever coefficient of friction I'm expecting to find, if I multiply that by 9.8 meters per second squared, that's what I should see as the slope of my graph. So then my graph also should have a y-intercept, because in this equation, we have a plus going on. There's a plus something. And these are things that aren't changing in my experiment. The coefficient of friction is not changing. The acceleration due to gravity is not changing. The original mass of the block is not changing. And so that means that those things are that y-intercept for my equation that I can actually calculate theoretically. I can say, oh, in theory, if the coefficient of friction of a wooden surface and another wooden surface is this a value, I can calculate what this y-intercept should be. One thing you want to double check is that your masses are in kilograms. If they are not in kilograms, then they don't play nicely with newtons, which I know that everyone's forces are in, because that's what we get from the force probe. So that's a thing to double check. But from this, we can say, aha, my slope is equal to the coefficient of friction times the acceleration due to gravity. And my y-intercept is all of these numbers multiplied together. And so I can predict what those will be. But that also means that I can say, well, if my slope equals a number, I can divide that number by g to get the coefficient of friction. So this means that I can actually predict what the coefficient of friction will be. This would be my experimental coefficient of friction, which I can then compare to the theoretical coefficient of friction that we have from our textbook citation. So it's theoretically supposed to be 0.2, but we can actually find out experimentally by taking our slope and dividing it by g. Similarly, if I take my vertical intercept, I can also get a coefficient of friction where I say, okay, vertical intercept, I'm going to divide that by g. So divide it by g. Okay, that makes g on this side go away. And then I'm also going to divide it by m original, which I'm trying to x out. Okay. And then, so that'll be divided by g. And I'm original. So that I can say, I can also find my my experimental coefficient of friction by using the vertical intercept, by using my y-intercept. And so this is how we get experimental values in science. We know if I graph this thing on the y-axis and this thing on the x-axis, my slope has a meaning, and I can use that meaning to actually describe what is happening. So you are going to be concluding by actually talking about your conclusion and what your experimental coefficient of friction is. And you're going to be able to compare it to the accepted scientific context that we actually set up and described here in our research design section. One last thing that you're going to include in your conclusion is the accuracy and precision of your results. And I'm going to quickly go over this. You can look back at your summer homework. You can also find lots of good resources for this online. But accuracy is how close a value is to the answer value. So like here, something that's accurate is close to the bullseye. And precise is how close the value is to itself, to the repeated measurements that we do. And we have a couple of different ways that we can think about that. There's more in that back in Unit 1. But how we address this from our laboratory standpoint is we look at the random error. And random error is about how close together our data are, how reproducible they are. And so if I had a whole lot of statistical uncertainty in each of my data points, that means that I probably have a lot of random error. Likewise, if my measurement uncertainty is quite large, like maybe it was in this lab in your force measurement uncertainty, you might have a lot of random error. It's not a judgment of how good or bad your lab is, it's just a description of your results and how they can be used to inform predictions, whether it's a precise prediction or whether there's a larger amount of random error and a larger amount of uncertainty then in that prediction. And so we can look at that by looking at the size of our error bars, by looking at how spread apart the maximum and minimum lines are, and then the uncertainty on the slope of our answer, and if we have any outliers. And so it really tells us about how precise our results are. If I have a small percent error, small uncertainty on my slope, percent-wise, then I have small amount of random error, which means more precision in my lab. Then, looking at systematic error, that's when something is going wrong sort of consistently that maybe I haven't fully planned for or taken into account when I set up my lab. And again, it's not that you're doing a bad job or that it's wrong. It's just something that allows us to quantify how certain we are of our results in terms of whether they're accurate based on what we think they should be. And so we look at the y-intercept or the slope to see if it's shifted from what we had expected in terms of the physics relationships. And that tells us about the accuracy. So if I have a slope that I expect to be 0.5 and I get an answer that says 0.6 plus or minus 0.2, well, 0.5 is actually within that. So you need to consider your uncertainty when you're considering whether or not you have systematic error. Because if your expected value is actually within the uncertainty of the value that you found, that you calculated in your experiment, then you can say, oh, I have an experiment that is accurate. It has low systematic error. And so you are going to be describing how much random error and how much systematic error you have based on your results. And so as you do this, I'm going to advise that you take a little time to talk together as a group and work on making sure that you understand, what do we expect our slope to be? What do we expect then our coefficient of friction to be? And then lastly, I just wanted to point out that again, I have this rubric from IB that you can use, and I have an in-depth checklist that is from me and other IB physics teachers that, again, it's very in-depth, but if you're like, man, I want lots of detail, this has it, and you should use it to help you write your IA.